In our last video, we looked at what it meant to have congruent triangles. But today and in our next video, we're going to look at some of the almost shortcuts that we can use to prove the triangles are congruent. So if we know that all angles and all sides are all congruent between two triangles, absolutely we know those triangles are congruent. But what if we knew just about the sides, or just about the angles, or a combination of the two? So our two scenarios that we're looking at today are what if we know all of our sides and what if we know all of our angles. So we looked at a quick demo for this when we were doing our class meeting. And if not, again, go back and check out the first 2 pages of that demo that you can link to through this folder's tasks. And you notice if we were given 3 sides of a triangle, we could make a congruent triangle. It didn't really matter how it was twisted around. So if we know that all sides are congruent, that's enough to prove the triangles are congruent. So let's go ahead and mark our 2 congruent triangles. And we're going to mark our sides so that triangle ABC is congruent to XYZ. So that means side AB and side XY would be congruent. So let's give them a single dash mark. And then we know BC and YZ would be congruent. So BC and YZ. And then our third set, we have AC and XZ, so they get their third congruent mark. So think back to what we looked at the demo. If we only knew about the angles, well, would that be enough to prove our triangle's congruent? And that's where we have a problem. So I know one of the types of triangles I have, which has all 3 angles congruent no matter what, is an equilateral triangle. So I could have a little tiny equilateral triangle and all of its angles have to be equal. And since all the angles add up to 180, each angle is always 60. But couldn't I draw a bigger version? Like something like this, which is still all 60-degree angles. So just knowing the angles, unfortunately, just isn't enough. Technically, what this is these aren't, or they're not necessarily congruent, but let's spell correctly, but they are similar. And this is actually something we're going to explore in our next unit. So keep that in the back of your brain. Unfortunately, these just aren't the same size. And part of our definition for congruent triangles is we have exactly the same kind of shape, so the same kind of triangle, and exactly the same size. And these very clearly, one's smaller, one's bigger. So we can prove that triangles are congruent then just with the sides. So one of the things that we've done before to actually find lengths, to find distances, is use our distance formula. So we're going to use our distance formula to determine whether or not we have 2 triangles. And I don't know the correct organization for these yet, but triangle PQR and triangle XYZ kind of are 2 different sets of points. And so let's actually find distance formula on this. So PQ, and again, it wouldn't be a bad idea to actually write down your points, because when we did this before, again, it's all about keeping the correct order. So let's do the distance formula for this. So x1 minus x2, so I'm going to do 5 minus a negative 3, all squared, plus negative 4 minus 7. And again, the order is less important as keeping it consistent through your entire problem. And so simplifying this out, we'll have an 8 squared, and negative 4 minus 7 actually gives us a negative 11. 8 squared is 64. Negative 11 squared is 121. And then 64 plus 121, 185. Square root of that. And I'm not going to worry about simplifying this, because if we're getting out the same number under the radical for any of these, then that's enough for us to prove we should get the same answer for the distance. Alrighty, QR, again, I would suggest writing your numbers down. And we have 0, 2. And then we plug it into our distance formula. So negative 3 minus a 0 squared plus 7 minus 2. And actually, I find sometimes if I line up my points like this, kind of top to bottom, it helps me line things up even easier. Okay, so we have -3 minus 0 is a -3, again squared, plus 7 minus 2 is a 5. Alrighty, so that gives us a 9 and a 25, which is going to give us a 34 square root. Again, don't worry about simplifying on this. That's enough to compare. And then PR. So we have the points 5, -4, and 0, 2. Distance formula, 5 minus 0 squared plus -4 minus 2 squared. Simplify them out. We get a 5 squared, and we have a -6 squared, otherwise known as 25 plus 36. Again, notice every time I'm squaring a negative number, it always comes out positive. Careful with your signs. That's going to give me a 61 square root. So if I know my triangles, or if I find that I get the same exact answers out for the sides and the other groupings, then I know that those triangles could be congruent. So I'm going to change my color, because why not? So XY. And again, if you want to pause, or if you want to, work these out and then fast forward to being able to check your answers, go for it. Alrighty, so -2 minus 9 squared plus -1 minus 7 squared. That gives us a -11 squared plus a -8 squared, otherwise known as 121 plus 64. And I'm noticing that is exactly what we had for segment PQ. We have the square root of 185. So I know that those are congruent. I'm actually going to draw a line so I know which ones. Okay, YZ. We have the points 9, 7 and 3, 2. Distance formula, 9 minus 3 squared plus 7 minus 2 squared. That gives us a 6 squared plus a 5 squared. And actually, that's the same thing that we were working on with PR. So we have a 36 and a 25 under our radical. We already did the math. So that comes out to square root of 61. And so these two match up. And then XZ, if these are congruent triangles, it should be the same length as QR. So let's test it. So XZ, we need our points -2, -1, and 3, 2. Distance formula, -2 minus 3 squared plus -1 minus 2 squared. Gives us a -5 squared plus a -3 squared. Square those out, we get a 25 and a 9. And now we're getting the same values we were working with in segment QR. Whole thing comes out to square root of 34. So indeed, everything matched up. Now things were kind of tweaked around a little bit. So our triangles are definitely congruent. Our reasoning, well, 3 of our sides equal 3 of the sides. And if all we need are the side lengths to prove these congruent, well, then we have congruent triangles. So let's see here. All right, so let's do our congruent statement now. Now we need to be careful with this because our names may be out of order and we want to make sure that we're matching up everything so we can write out our names properly. So I'm going to start out with my first triangle. We had side PQ and then QR. So if I think about that, it says PQR. I'm actually going to go ahead and write my other expression backwards, RP, my third segment. And so that might help me rearrange my orders a little bit better. And I'm noticing the same kind of thing was sort of happening with my second set of values. So I had XY, I had YZ, and then I had XZ. So something in there is going to be flipped around. So let's actually first look at, where we have this kind of overlapping happening. So we have our first thing, XY and YZ. So we have the Y's matching up. Well, we have the same things happening here with the PQ and QR. So that means I think that my Y should probably be with my Q. And let's see if that keeps on working. QR, that was with our YZ. So we would have YZ, and then RP or PR, excuse me, I have put those backwards. Our QR was actually matched up with our XZ. So actually the Q, that can't be the Y. That's going to have to be the X. So that means Q now matches up with, let's see here. So the QR matched up with the XZ. There we go. And then do we still have the Z matching up with an R? Yep. So that's our ZY. So we know that triangle PQR is congruent to triangle YXZ, going in the same order. And the other thing that could also help too, if you're not able to figure it out, just given your links, try graphing it out on a piece of graph paper if you're given those points, and see which one of those kind of directions you need to name things in. Alrighty, so the last piece that we need to talk about is where we can graph congruent triangles. And actually, let me change over to red because that'll pop better on the graph. So the question here is, where can I draw point C? Technically, it's C prime with that little apostrophe on it, so that I'm drawing a triangle that's congruent to what we were given. So we were given triangle ABC, and then we're going to draw a congruent triangle. This is called A prime, B prime, C prime. And we use these sometimes when we talk about transformations, which you've seen before. And we'll do a review on this towards the end of our class. But A matches up with the A prime or A apostrophe, and that just makes it a little easier for us to match things up. I can also see from the graph, we have segment AB up here, which has 3 units, and we already have a starting point for this. So they already gave us one of our segments. I want to go around in the same order. So if my first triangle was named as ABC, I'm going around in this order. I'm going down AB and then around to C. So let's see, I can't quite go in the same order with just with where my new A prime, B prime segment is. So I'm going to have to go around, but then right. And so I just want to make sure I go the same amount of spaces. So let's see, segment BC is 1, 2, 3, 4, 5 spaces. I always count the spaces on these. So I'm going to draw over 1, 2, 3, 4, 5 and put my new C prime there. And then I should be able to connect this. And now I have a congruent triangle. So we put C prime at the coordinates 1, -5. And it's really just counting out the distances. If you have slanted lines or diagonal lines, again, count how far over, how far up you have to go. Let's try another one. So example 3. We're going to draw point D so that we have triangle ABC congruent to triangle CDA. Now this one's a little different. You'll notice, and I'm going to go ahead and write this down below. Actually, let's write over here. So triangle ABC has to be congruent to triangle CDA. We've got some things in common. So our common things that we've got here, we have an AC in the first triangle name, and we have that AC, but what happened to it? It got flipped around. So if it got flipped around the name, then likely we're going to have to flip the triangle around when we draw it as well. So let's see here, save. So let's try this. So triangle ABC in our first one. So ABC. I went around to the left and then back. So if I'm going to do CDA, that means I'm starting at point C. I'm going to have to go around in kind of the reverse order. So my other triangle is going to look something like this. So that's going to give me a hint as to where I'm going to draw things. So my new line, my first new side that I'm going to have to draw, if I started A to B, well, count how far you had to go to get there. I had to go over 5 and down 2. So I'm going to totally reverse that. I'm going to go to the right 5 and then up 2. And again, count your spaces, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then up 2. So that's going to be the correct spot for D. And again, if you connect the lines, again, my previous arrow that I used to just kind of map things out, it wasn't perfect, but it gave me a good idea of where I had to look for. And you'll notice this actually makes a really nice picture of a parallelogram, which we'll study in a little bit. So for this one, D is at the coordinates 4, -1. Alrighty, same sort of thing with number 4. Again, things are reversed on us. So figure out your order and then reverse it up. So if I go triangle A, B, C, again, starting at C, but going in reverse order. So instead of going down, I'm going to go up and over. Segment AB, 1, 2, 3, 4, 5, 6 spaces. So I'm going to go up 6 spaces from C to do that in reverse. So 1, 2, 3, 4, 5, 6, actually right at the top of the graph. And then it gets connected back. And so here's my new triangle with point D stuck at the top. Now, it's not the only place that you could put D, but it's the most likely. We could also put a D, and let me change color. I could put D somewhere over here, but it would involve, instead of counting straight down, I would have had to twist things around and maybe go up at an angle to be able to get that same length. It's a whole lot easier to just do the D up in the first quadrant for this one. So yeah, there may be more possible answers that I don't necessarily show. That doesn't mean they're incorrect. So the D spot that we found for this is over 3 and up. 1, 2, 3, 4, 5, 6, 7. So at 3, 7. As always, feel free to rewatch or pop into Zoom if you have questions. See you later.